Welcome to today's distinguished lecture. So we are very happy to host a talk of Professor John Ellis, who is our long-term colleague and friend and a contributor to the success of our institute. I would like to ask the participants to use the Q&A button for their questions, which is on the bottom right of your screen, or raise your hand, which is next to it, with the button next to it, in case you would like to voice some questions. So let me introduce our speaker today. Professor Ellis is the British theoretical physicist who is currently holding the Clerk Maxwell Professorship of Theoretical Physics at King's College in London. He obtained his PhD in Cambridge and held postdoctoral position in SLAC and Caltech, after which he moved to CERN, where he worked for several years as the host of as the leader of the theory division. Professor Ellis' interests focus on the phenomenological aspects of the particle physics and the actual connection to the astrophysics, cosmology, and the gravity. Much of his work is related directly to experiments, especially nowadays to the LHC, interpreting the results of searches of new particles and exploring the physics which can be done with the future generation of the particle accelerators. In 1976, the prediction Professor Ellis made led to the discovery of the gluon in 1979, and he was one of the first to study the properties of the Higgs boson and predicting how it can be produced and discovered. He authored over 1,000 scientific papers with over 80,000 citations in total, and many years he was active in the efforts understanding the Higgs particle, which we discovered at CERN, and trying to see whether it matches the prediction of the Standard Model or some model which is the extension of the Standard Model, such as, for instance, supersymmetry or other possible physics theory, which would give us at least a dark matter concept. So today, Professor Ellis kindly agreed to give us a lecture on the anomalous magnetic moment of the muon, on the famous problem colloquially known as G-2, which well might be an actual portal towards the new physics beyond the Standard Model, which we're all trying to find for the last several years. So, John, thank you very much for joining us today, and the floor is yours. Thank you.
Okay, thanks very much. Thanks very much for the invitation to come to HKUST, even if only virtually. And I sincerely hope that normal scientific exchanges will be possible again in the near future, and I'll be able to visit you in person soon. So, as Kirill mentioned in the introduction, the anomalous magnetic moment of the muon is currently attracting an enormous amount of interest because it may be a portal towards new physics beyond the Standard Model. And that's illustrated in this cartoon on the first slide, where you see a muon. At the top, you see a photon coming in. And in the middle, you see a blob. And that blob is possible new physics, which is going to contribute to the magnetic properties of the muon. And I want to tell you where we are with the theory and the experiment of this observable, and talk a little bit about the prospects for resolving the puzzle of the anomalous magnetic moment of the muon in the future. So, a lot of the current excitement about the anomalous magnetic moment, or G-2 as we call it, originated with an experimental result last year announced from Fermilab. And in this picture here, you see the arrival at Fermilab of the magnet that was used in that experiment. I like the sky behind it. I'm not quite sure whether that sky is the dawn of a new age of physics beyond the Standard Model, or the dusk of the sun setting on the Standard Model. Anyway, I think it's a nice image that summarizes our hopes for G-2. Now, this is actually an old story, and one can trace it back over 94 years through 8 experiments and many theoretical contributions. And I can't do justice to all that story in the course of this talk, but I'll do my best. So the theory really the story really starts back in 1928. And that's when Dirac wrote down his quantum theory of the electron. And in particular, he wrote out his famous equation. And analyzing his equation, he realized that it predicted that the electron's magnetic moment, G, would be equal to 2. I should perhaps mention that at the time, the electron was the only fundamental fermionic particle known. So Dirac was very excited by this result, and he wrote that this was really an unexpected bonus for me, completely unexpected, to be able to predict the electron's magnetic moment. Now, I would also like to just go back to the previous year. In 1927, Dirac wrote another fundamental paper on the quantum theory of the emission and absorption of radiation. And the development of quantum electrodynamics, in fact, all of quantum field theory, can somehow be traced back to that paper. And the machinery of quantum field theory enables us to calculate quantum corrections to Dirac's original result and find that G is actually not equal to 2. And that's what we call the anomalous magnetic moment of the muon. So here, just for the record, I've shown you copies of the front pages of Dirac's famous papers from 1927 on the left and 1928 on the left and 1927 on the right. And here in this inset, you see the way that Dirac wrote out his equation, which doesn't look quite the same as the way we'd write Dirac's equation now, but it's equivalent. So how come you get a magnetic moment for an elementary particle like an electron or like a muon? So, of course, we all know that a solenoidal current acts like a magnet. And here I've got a little picture, a simple solenoid, and the magnetic field that it generates. Now, elementary particles like the electron or the muon spin, and the spinning charge distribution acts just like a solenoid. And since it acts like a solenoid, it can generate a magnetic dipole moment in the same way. And the quantum effects that I mentioned a moment ago modify the charge distribution. And in that way, they generate the anomaly in the magnetic moment. Okay, so we've got an electron, we've got a leading order prediction that G is equal to 2, and quantum mechanics, as we'll see in more detail later on, gives us the possibility of generating an anomaly in the magnetic moment. What we don't yet have is the muon. So the story of the muon starts with cosmic rays. So cosmic rays, of course, were discovered a bit over a century ago. These are energetic particles or nuclei from outer space, which hit the upper atmosphere. And when they do so, their energy is converted into lots of other particles. And it was in the showers of particles produced by cosmic rays that, for example, Dirac's antiparticles were first discovered. And it was also in those cosmic ray showers that the muon was discovered. So that happened in 1936. So Anderson and Neddermeyer observed particles in the cosmic rays that behaved differently from electrons and protons. These new particles were both positively and negatively charged, and their tracks curved in a magnetic field, but in a different way from electrons and a different way from protons. And that difference in curvature implied that these new particles had a mass which was intermediate between the electron and that of a proton. And in fact, of course, we know that the mass of the muon is about 100 MeV, about 200 times the mass of the electron. Now, it's worth mentioning that there was some confusion initially because just before the discovery of the muon, Yukawa had predicted the existence of the pion. It was thought that these Anderson-Neddermeyer particles might be Yukawa's meson. But of course, that's not the case. It was soon discovered that the muon does not have strong interactions. It only has electromagnetic, and as we'll see later on, weak interactions. So the discovery of the muon was a big surprise. And there's this famous quotation from Rabi when he heard the discovery of the muon: "Who ordered that?" So he was thinking of when a group of physicists go to have lunch in a Chinese restaurant, a lot of dishes arrive, and there's one dish that nobody was expecting. So who ordered that? And I think the answer to that question is we still don't know. Of course, following the discovery of the muon, many other unexpected elementary particles showed up, the tau lepton, quarks, and so on and so forth. So Rabi's remark could also be applied to other particles, but initially it applied to the muon. So what do we know about the muon? So it has the same electric charge and weak interactions as the electron, but it weighs about 200 times more, mass of 100 MeV or so, compared with the electron mass of half an MeV. It decays through the weak interactions with a lifetime of the order of a microsecond. And this means that muons produced in cosmic rays, by the collisions of cosmic rays in the atmosphere, can penetrate to the Earth's surface. And in fact, the flux of cosmic ray muons at the Earth's surface is about 1 per square meter per second. And the very energetic muons can penetrate kilometers of rock and are observed deep underground. So, as you know, we have a so-called standard model of elementary particles. And I've outlined here in red the place of the muon in this standard model. So the top right, we have the electron. The muon, as I mentioned, has identical properties apart from its mass with the electron, and there's a similar heavier particle called the tau. When the muon decays, it decays into an electron and a couple of neutrinos. So we've got this bunch of particles which don't experience the strong interactions. And then, of course, the fundamental constituents of strongly interacting matter are the quarks over here on the left. So the muon participates in electromagnetism, obviously, through its charge, and the weak interactions through its decay, but not the strong interactions. Okay, so we've got the muon now, and we have quantum electrodynamics. So for some time, people didn't know how to calculate in quantum electrodynamics. But then in the 1940s, Schwinger and others figured out how to do the calculation. And in 1947, Schwinger calculated the anomalous, the leading order anomalous contribution to the magnetic moment of the electron, or equivalently the muon, in QED. And he got the answer, alpha over 2 pi. And Schwinger was very proud of that calculation. In fact, he had it written on his tombstone. So you see here, written in bold at the top is his calculation of the anomalous magnetic moment. then his name, and finally his wife's name. Personally, I would have written them in the opposite order, but anyway, that was Stringer's choice. Now, the calculational tools offered by quantum electrodynamics enabled more complicated calculations to be done. In particular, it was possible to calculate the second-order contributions to the anomalous magnetic moment of the electron and the muon. And on this slide, I'd just like to make a shout out for André Petermann, who was the first person to calculate correctly the second-order contribution to the anomalous magnetic moment of the muon. That was in 1957, and here's his result, as you see here. I should mention that there are a number of other people who contributed to this calculation, but Petermann was the first person to get all the terms correct. So Petermann is somebody who's not particularly well known, but actually he made two other really fundamental contributions in theoretical physics. He was a co-inventor with Stuckelberg of the normalization group, and he was actually the first person to publish the idea that mesons might be made of constituents, things that Gell-Mann called quarks. Shortly afterwards, the first experimental measurement of the anomalous magnetic moment of the muon was published by Lederman and collaborators. So their paper was written in 1957, published in 1958, and their result agreed well with the calculation of Petermann and others. Lederman then actually suggested to CERN that it do a more accurate experiment to measure the anomalous magnetic moment of the muon. And here are some pictures of the team that did that first experiment at CERN. So down here, the bottom right is their magnet. Up here is the experimental team sitting on the magnet. And well, one of the people you may recognize, that's Georges Charpak, who later on went on to win the Nobel Prize for his contributions to the development of particle detectors. So the principle of this experiment was to inject muons into the magnet, and then in the magnetic field, the spin of the muon would precess, and as the spin precesses, it carries with it the magnetic moment, and the muon then decays into electrons, and the distribution of the electrons depends on the direction of the muon spin. So in that way, you can measure the precession and hence the anomalous magnetic moment. And they got a result which had an accuracy of 0.4%. Now, subsequently, experimentalists figured that they could get more precise results if they used storage rings, so they could keep the muons there for a longer period of time. That would enable them to get more statistics and make a more precise measurement of the rate of precession. So here's the basic principle of the storage ring experiment. You start off with a beam of protons. They hit a target. They produce pions. The pions decay into muons. The muons, as we've discussed, are like tiny little magnets spinning on their axis like tops. You inject the muons into this storage ring. As the muons go around the storage ring, their spin precesses at a rate proportional to the anomalous magnetic moment. They decay into electrons, and you measure the distribution of those electrons. So the first storage ring experiment was done at CERN in the 1960s. And here's a picture of the experiment under construction. And that indeed gave a more precise measurement of G-2 with an accuracy of, as you can see, 200 or 300 parts per million. So here, the comparison with the theoretical calculation required inclusion of light-by-light scattering. I'm not going to say very much about light-by-light scattering, but I'd be very happy to respond if you have some questions about it. So, meanwhile, theorists were doing more complicated calculations, and here I introduce some of the leading figures in those calculations. There's Kinoshita on the left and Loutrip on the right. And here are diagrams that they calculated. Here's at least part of their result. And this, by the way, is a light-by-light scattering diagram, which needs to be included in order to get consistency with the experimental result. They went on to do more complicated calculations, and these are diagrams that contribute at fourth order in the fine structure constant. And again, those are essential for comparison with the experimental measurements. Now, in parallel to those improved theoretical calculations, CERN embarked on a second storage ring experiment, which took place mainly in the 1970s. So here you see the magnet system of that experiment, which is rather larger than the previous one. The reason why it's larger is because they worked at a very specific so-called magic energy. And so the energy of the muon determines the size and the magnetic field that you need in order to keep the muons circulating in their orbit. So the point of this magic energy is that then stray electric fields do not contribute to the precession of the muon. The only contribution to the precession comes from the anomalous magnetic moment. And if you design carefully the magnetic field so that it's orthogonal to the orbit of the muons, you get a very simple expression for the rate of precession directly related to the magnetic moment. And here in the upper right, you see a picture of the electron signal that you get from the decays of these precessing muons. You get this characteristic wave structure. And this second CERN experiment got an accuracy in the measurement of the anomalous magnetic moment at the level of 8 parts per million, so much improved over the previous experiment. So that took place in the 1970s. So what happened next? Well, what happened next was people got interested in possible theories beyond the standard model, and in particular in the theory of supersymmetry. I'm not going to go into great details in supersymmetry. It has many theoretical virtues. It stabilizes empty space. It made a successful prediction for the mass of the Higgs boson and couplings. It plays a key role in many advanced theoretical ideas, but in particular, it could make a significant contribution to the anomalous magnetic moment of the muon. And this is a theme that we'll be returning to later on in the talk. So the minimal supersymmetric extension of the standard model just basically doubles the number of particles. It postulates additional, as yet unseen particles with the same internal properties as the known ones, but differing amounts of spin. And outlined in black here, I've got the particles in that supersymmetric model that could provide the astrophysical dark matter. And in red, I've outlined the particles in supersymmetry that could contribute to the anomalous magnetic moment of the muon. So I got first interested in the supersymmetric contribution to the anomalous magnetic moment of the muon 40 years ago. We wrote with John Hagelin and Dmitry Anomalous our first paper on G-2 in supersymmetry. So the leading order contributions given by a relatively simple set of diagrams. I should say that we were not the only persons to do such a calculation in 1982. This is just my own personal landmark. Now, in the 1980s, Brookhaven Laboratory in the US embarked on another experiment to measure the anomalous magnetic moment of the muon. And this experiment took something like 20 years to produce its final result. The magnet for this experiment you can see here, painted blue, and inside we have the electronics that was used to measure the decays of the electrons produced by the precessing muons as they went around the ring. And here are some of the leading lights of that experiment. It's worth noting that some of the people in this Brookhaven experiment were also in the earlier CERN experiments. I mentioned in particular this guy in the middle here, Francis Farley, who was the grandfather of a schoolmate of my son. So I got to know him quite well. So what did the Brookhaven experiment find? It found an interesting discrepancy with standard model calculations. So the Brookhaven experiment measured the anomalous magnetic moments of both the positive and negatively charged muons. Here's the average. And over here on the right, we have theoretical calculations. Now, at the time, it was not possible to do an ab initio calculation. Instead, what people did was they did a calculation which relied on data from E plus E minus annihilation into hadrons to calculate that sort of egg-shaped blob that I had on my first slide. Now that egg-shaped blob is what we call the vacuum polarization diagram, and I'll be discussing that in more detail in a moment. So those calculations didn't agree very well with the Brookhaven experiment. The accuracy of the experiment, by the way, was 0.47 parts per million. So in the early 2000s, I wrote another paper with Dimitri Anomalous and Keith Olive this time, seeing whether supersymmetry could explain this discrepancy in the anomalous magnetic moment. So we found that was possible if supersymmetric particles weighed less than about a TeV or so, that's the shaded pink region here. And interestingly, it was also possible to explain the astrophysical dark matter simultaneously with G-2. So the dark matter region is shown as this sort of greenish blue strip here. And as you can see here, getting the anomalous magnetic moment of the muon correctly required supersymmetric particles weighing a few hundred GeV, which of course was good news because that would be within range of the LHC. So following on, later in the 2000s, Kinoshita and collaborators did even more detailed calculations to fifth order in the fine structure constant. And here you can see the plethora of diagrams that they needed to calculate. So a couple of years ago, a large group of theorists got together to make a comprehensive review of calculations of the standard model contributions to G-mu-2. And they included a very careful discussion of all the uncertainties, particularly in the calculation of the leading order vacuum polarization, that sort of egg-shaped blob that I had on the first slide. So here is a somewhat more scientific representation of that blob. If you cut that blob through the middle, then you've got this diagram, which is shown here. And this illustrates the connection between that blob and E plus and minus annihilation through a photon to make hadrons. Now, I remind you that the mass of the muon is about 100 MeV. And because it's got low mass, this means that the most important contributions to that hadronic blob have relatively low masses, less than about a GeV. And that's illustrated here. The yellow shows, in the pie chart, shows you the fraction of the theory calculation that comes from low mass resonances, specifically the rho and the omega resonances shown here. They also make a very important contribution to the uncertainty in the calculation, shown as this yellow piece of pie over here. There's also a contribution from resonances between 1 and 2 GeV, but higher energies, higher mass states make a less important contribution, and they're also under very good theoretical control using our theory of the strong interactions, perturbative QCD. So this shows a comparison of calculations of that egg-shaped blob. So at the bottom here, we have the calculation which is recommended in this theory review article. So their recommendation agrees with a couple of previous determinations. And it also agrees with this hybrid data lattice calculation, which I've outlined in black. So the gray band is the preferred theory estimate. And over here in yellow, we have the band favored by the Brookhaven experiment. Now, perhaps I should have clarified. This theory review was done in the year 2020, anticipating that there would soon be a result from the Fermilab experiment. And this vertical gray band here indicates what should eventually be the uncertainty in the Fermilab experiment. Now, up here in blue, we've got some calculations based on the lattice, which most of them have rather large uncertainties, and they span the range between the Brookhaven measurement and the theoretical calculation using E plus E minus data. But there is one lattice calculation that claims a smaller error, and if there's time later on, I might comment on that. Okay, so the stage is now set for the Fermilab experiment. So I showed you earlier on a picture of the magnet arriving at Fermilab, and here you are with crowds of people greeting the arrival of the magnet. Perhaps I should have said earlier, that the magnet which was used in the Fermilab experiment was the same as the magnet used in the Brookhaven experiment and had to be transported over thousands of kilometers to get from Brookhaven to Fermilab to do the experiment. And here you see a bunch of flags of people participating in Fermilab experiments. And I note this one in particular. So by now, the experimental team had grown, and here is at least part of the Fermilab experimental team inside the recently arrived magnet. And here we are now with the experiment installed, the same blue magnet that we saw previously at Brookhaven, but different electronic equipment. So here are the Fermilab data. So again, you get this characteristic wavy signal of the muon to electron decays. And by measuring the frequency with which, the frequency of the waves, you get a precise measurement of the anomalous magnetic moment of the muon. So here's the result. So the Fermilab result is shown here in red, and it agrees very well with the Brookhaven result, which is shown in blue. At the moment, the uncertainties in the two experiments are similar. Eventually, Fermilab will have more data, more statistics, and a smaller uncertainty. It's perhaps worth mentioning that the dominant contribution to the uncertainty in the measurement is actually statistical. The systematic contribution is relatively small. So you can combine the Brookhaven and Fermilab results, and that's what's shown here in purple, and that disagrees with the standard theory estimate by 4.2 standard deviations. So that doesn't quite reach the standard particle physics standard of 5 sigma for an experimental discovery, but it's getting pretty close. So that result was announced about a year ago, and immediately there was a tsunami of theoretical papers. So for the first month or so, I tried to keep track of the papers, what model they proposed, the names of the authors, and what other parts of particle physics they considered in their analyses. Now, in this spreadsheet, they are colored according to what was the theoretical interpretation that they proposed of the data. So some people proposed leptoquarks, some people proposed an additional Z prime boson, extra Higgses, or supersymmetry, shown here in green. So let's return now to the anomalous magnetic moment of the muon in supersymmetry. So these are the two leading order diagrams which I showed you earlier on that we've done a first calculation of back in 1982. So here I just wanted to mention a couple of complications in these calculations. So these calculations involve the supersymmetric partner of the muon, called the muon, and they involve neutralinos. These are the neutral particles that one of them could provide the astrophysical dark matter. In fact, there's two different muons because there are different supersymmetric partners of left-handed and right-handed spinning muons. And there are actually 4 different neutralinos corresponding to the supersymmetric partners of the Z boson, the photon, and 2 neutral Higgs bosons. So you have to consider the mixing of all these particles, and that explains all these indices that I've introduced here. I should mention that in addition to a diagram involving the muon and the neutralino, there are also diagrams involving the supersymmetric partner of the neutrino and charged supersymmetric enos, but those don't play such an important role, and I'm not going to discuss them here. So you might be wondering whether supersymmetry can actually explain the discrepancy in the anomalous magnetic moment of the muon, given the fact that searches at the LHC give very strong lower limits on the masses of strongly interacting supersymmetric particles, like the partners of the quark and the gluon, called the squark and the gluino. We know that they have to weigh more than 1 or 2 TeV. And as I mentioned earlier, if you want to explain the discrepancy in G-2, you need supersymmetric particles which weigh at most a few hundred GeV. But the point is that the particles that enter G-2 are not the same as the ones for which the LHC has the strong limits. And it's perfectly consistent with the LHC data that the neutralino and the muon weigh a few hundred GeV, which would be what you would need in order to accommodate the G-2 result. So these plots are taken from a paper that we wrote a couple of years ago. I'll come back in a moment to more up-to-date calculations. but in supersymmetry, it's certainly possible to explain the G-2 discrepancy. So that was, as I said, a few years ago. Since then, there have been some additional LHC constraints on supersymmetry, which we didn't incorporate in our analysis. In particular, there's been a couple of results from the ATLAS collaboration, looking specifically for light electroweakly interacting sparticles, the seleptons, the Muon, and the selectron, the supersymmetric partner of the electron. And these are some plots from ATLAS analyses. So here they looked generically for Muon and selectron decaying into a dark matter particle. And here they did a dedicated search where the mass difference between the selepton, for example, the Muon, and the dark matter particle is small. Now, what you see here is that although generically they would say, well, the Muon has to weigh more than a few hundred GeV, there is in fact a region of parameter space where the Muon could be much lighter, even potentially as light as 100 GeV. And this option for light supersymmetric particles has also survived this other dedicated ATLAS search shown on the right-hand side. So the LHC limits on the Muon are very much weaker than the LHC constraints on the squarks and the neutrinos. So we wrote a couple of papers last year where we analyzed possible supersymmetric contributions to the anomalous magnetic moment of the Muon in different supersymmetric models. So one of them is shown here, labeled CMSSM, and another one shown here in red is flipped SU5. So the CMSSM is the sort of supersymmetric model which was fashionable for many years, in which indeed there was a connection between the mass of the squark and the Muon, and a connection between the mass of the gluino and the neutralino. And in those models, you cannot get a big contribution to G-2. In red here, I show a calculation in a model where the connections between the masses of the squarks and gluinos on the one hand, and the Muon and the dark matter particle, the neutralino, on the other hand, where those connections are relaxed. And what you see here is that in that case, you could get a much larger contribution to G-2. And this larger contribution could certainly explain much of the discrepancy between the standard model calculation and the data-driven calculation of, between the experiment and the data-driven theoretical calculation. Now here in blue, I also mentioned this lattice calculation, which has caused a bit of a stir recently, where they claim that these data-driven calculations may not be quite correct. And they say that maybe the discrepancy between the standard model and the experimental result is smaller than what other people believe. And if they're correct, that's certainly something that one could explain in a supersymmetric model. So what's the way forward for the anomalous magnetic moment of the Muon? How are we going to learn whether the discrepancy between standard model calculations and the Brookhaven and Fermilab results is due to new physics or not? So one element, of course, is that Fermilab is continuing to make more precise measurements, and we can expect relatively soon to get some new and more precise results. In parallel, there is a proposal at CERN to make a different measurement of that egg-shaped blob Now, when you're doing E plus E minus annihilation to hadrons, you're looking in the time-like region at the annihilation of the time-like photon into physical particles. But actually what enters in the calculation of G minus 2 is a space-like photon, like a photon that is exchanged when you scatter a muon off an electron. And so there's this proposal at CERN called Muon, which is going to do precisely that. It's going to scatter 150 GeV muons on electrons, and it's going to measure that blob, but precisely in the kinematic range where it's most relevant to G minus 2. So they're going to be doing a test run this year, and if that's successful, then they plan to go on and make a very accurate measurement. And this is a simulation of how well they should be able to measure in the future. There's also another experiment being prepared at JPark in Japan. So some people worry a little bit that the Fermilab and Brookhaven experiments rely on the same experimental technique. So they both of them use the same magnet, they work at the same magic energy, they use the same trick to get rid of the electric field. It would be nice to do an experiment using an independent experimental technique, and this is what is now under preparation. In this, you generate a low energy, ultra cold muon beam. You accelerate it to 300 MeV, and you inject it into a tiny storage ring. No, it's about this size, not the many meters of size of the Brookhaven and Fermilab experiment, 66 centimeters. So, what's the future for G minus 2? So I think we shouldn't lose sight of the fact that the experiments are fantastic. The accuracy is amazing. The accuracy at the level of 1 part in a billion. And at the level of 1 part in a billion, there is agreement between theory and experiment. Of course, there is a discrepancy also at the level of 1 part per billion. And as I've tried to describe, that could be a very exciting portal on possible physics beyond the standard model. Now, according to the conventional standard model calculations, there is a significant discrepancy, 4.2 standard deviations. But as I have highlighted, there is still a debate about that standard model calculation. I also showed you that many different theoretical interpretations have been proposed. I didn't do justice to all of them. Some of them connect the anomalous magnetic moment of the muon to B decays, and others, including in particular supersymmetry, connect the anomalous magnetic moment to models of dark matter. The good news is that there are more experimental results on the way from Fermilab, from JPark, from this Muon experiment at CERN. And I might mention also that there is work going on to measure the anomalous magnetic moment of the electron, which could also cast some light on what is going on. So we certainly live in interesting times. So here's my summary slide. The standard model is cruising along beautifully in its description of the visible matter in the universe. But maybe hidden in the iceberg is a problem with G minus 2, and it may be G minus 2 that sinks the standard model and takes us to a theory beyond, such as, for example, possibly supersymmetry. Thank you.
Thank you very much, John, for this very enlightening lecture. So I would like to invite people to ask questions or make comments, please. Just raise your hand or speak up if you like, please. perhaps then I can start with one question. So I was actually very astonished to see that the supersymmetry, let's say the comparison to the current ATLAS and CMS results can still accommodate for very light mass neutralino, and then therefore this can be an explanation, still a supersymmetric explanation for the for the anomalous magnetic moment. Do you think that by, let's say, the end of the LHC program, the direct sources such as Higgs to invisible will actually limit this? Because that's, I mean, Higgs to invisible, it's more or less the same mass range, right? By going low there in the mass, so eventually we probably can be excluding this.
Well, I'm not so sure of that, because Higgs to invisible decay is, that's possible for neutral particles that weigh less than, let's say, 50 or 60 GeV. But what I'm talking about here is neutral particles that weigh probably more than 100 GeV. So that there's a pretty nearly cast iron low limit on the mass of the neutralino, which comes from LEP experiments. And that's what's shown here as this yellow and gray band. And the region of supersymmetric parameter space where you could get an interesting large contribution to G-2 is really pushing up against that low limit. So, but that's still, like I said, masses of the supersymmetric neutral particles that weigh more than 100 GeV or so. Now, I think what is more promising is to somehow try to strengthen the LHC constraints in this sort of channel region down here. Now, this, of course, is very difficult because you're basically needing to look for relatively soft muons or electrons produced by the decay of this muon or this electron into a neutralino. But this is, I think, a region that I would focus on in the LHC searches.
Right. So the supersymmetric explanation for the anomalous magnetic moment can actually handle the neutralinos up to which mass? So you say it's around 100, maybe 200 GeV. Can it go higher? It can still be an explanation, or there is a limit when the supersymmetry is not fitting anymore?
So I showed here the range of masses that, the range of contributions to G-2 that we get in our particular flipped SU5 model. So in that case, we really need something which I would say is between 100 and 200 GeV. However, if you relax your theoretical assumptions, then you could go to larger masses. And that's illustrated here. So in this case, we found that you could go up to about 300 GeV for the neutralino and about 400 GeV for this muon. Now, I'm afraid we don't have an updated analysis using the latest LHC 13 constraints, but I don't expect it to be very different. And this is something that we are studying at the moment, but I'm afraid we just don't have results at the present time. So in general, I think the neutralino, the muon, would need to weigh less than about, let's say, 400, 500 GeV. So that's anywhere in this channel here, in this specific model that I discussed, it would have to be smaller, between 100 and 200.
All right, yeah, this is clear. Thank you very much. Questions, comments, please. So there are two online questions, but maybe we can just voice them. So if the authors can just speak up, would be easier. Maybe Luis, can you just voice your question? Okay, then I just read it. So Luis is asking for a comment on the relationship between the G-2 discrepancy and the possible violation of Lepton flavor universality. Would those two results, if confirmed, lean towards any family of models?
Yes, thank you, Luis, for that question. So there are models that attempt to explain both simultaneously. And one particular example is provided by leptoquarks. So I'm afraid I don't have a plot in this slide deck, but there are, perhaps for the general public, I just mentioned what a leptoquark is. So this is a boson that couples to both leptons and quarks. And those couplings to leptons and quarks may be different for electrons and muons, and if they're different for electrons and muons, that could explain the anomalies which are seen in B decays. So indeed, leptoquarks are among the favored interpretations of the G-2 discrepancy. And as you can see here in blue, many of the people who look at leptoquarks also consider B decays. So it is possible to explain both simultaneously in that framework. It's also possible maybe with an additional Z prime boson. I would say, though, that it's very difficult within supersymmetry, at least the sort of supersymmetric model that I've been discussing. The sort of model that I've been discussing could not explain the B decay anomalies.
Thank you. There is another question here, which I think from anonymous attendee. If the anomalous G-2 is confirmed, does it mean we have to abandon standard model entirely? Well, I don't think so. Or only modify it to account for this anomaly? And why has it taken this long to discover the anomaly? I'm just reading the question. Okay. So that's actually rather an interesting question. So it doesn't require us to modify the standard model. The standard model, would still be correct, but its domain of applicability will be limited, and there will be some instances where we need some additional physics to interpret the experiment. So the situation is a little bit like that with gravity. So Newtonian gravity works great. Okay, if I drop my cup, then it drops. And it's nothing, and I don't need general relativity to describe that. However, of course, we know that the orbit of Mercury precessed, to use a word that I've been using a lot in this talk, and that is explained using an extension of the Newtonian theory of gravity provided by general relativity. So what we're talking about here is not a modification of the standard model, but an extension of the standard model to include new particles with additional interactions. Then the really interesting part of the question is, why did it take so long? And indeed, I think this is a very interesting sociological or political question. So Brookhaven had this very good experiment, which produced its result in the early 2000s. They could have continued and got a more precise result, and we would have potentially known a decade ago whether or not this anomaly was for real or not. But for obscure bureaucratico-political reasons in the United States, they decided to move the experiment from Brookhaven to Fermilab, and this generated at least a decade's delay in obtaining the new experimental result. So that's why it took so long. Thank you, John. Just out of curiosity, so I look at this slide here, right? And of course, majority of the explanations are green, right, which leans towards the supersymmetry. What's your favorite, if not supersymmetry? Well, if we tomorrow figure out that all the candidates are way too heavy for that, so what is the plausible other explanation, the most plausible?
So I think I would go in the direction of leptoquarks, which have the virtue, as we discussed a moment ago, of also potentially explaining the B decay anomalies. So the B decay anomalies are currently hovering at a significance level comparable to that of G-2, let's say somewhere between 4 or 5 standard deviations. By the way, tomorrow there's going to be a new round of experimental results released, so no, I'm quite sure what's going to happen tomorrow, but today it's still between 4 and 5 standard deviations. So leptoquarks could potentially provide a unified explanation of G-2 and the B decay anomalies. And of course, they also predict new particles, leptoquarks, that could be discovered at the LHC. So I think that what I am going to be interested in seeing from you and other guys working on LHC experiments is not just analyses of lights, muons, but also pushing the searches for leptoquarks as far as possible.
Thank you. Cambu is asking, how sophisticated are the lattice calculations? Okay, Cambu, so you put your finger on the delicate point. So if you are dealing with a lattice calculation, you know, it's a discretization of space-time. So you imagine, let's see, do I have a So here you see a lattice, okay? So this lattice has finite size and it has holes in it, okay? So the holes tell you that the lattice does not calculate directly what's going on at short distances, and the finite size tells you that it doesn't tell you directly what's happening at very large distances. So if you want to do a complete calculation, you have to make an extrapolation to short distances and extrapolation to large distances. Now, there is this Bmw lattice calculation that makes a strong claim for the accuracy, not only with which they can calculate the lattice, but also that they can make the extrapolation. So there are other lattice groups that are more conservative. And in particular, they say, well, look, we can calculate at intermediate distances, so if you like, the sort of average scale of the lattice. But in particular, to go to large distances, we use the data to make the extrapolation. And they can also use the data to do the very short distances as well. And let's see. Yeah, so this calculation in black here, that's basically what they do. They use the lattice for the intermediate scales, but then they use data for the large scales and the small scales. And I think a lot of lattice people think that this may be the most promising approach for the future. So I don't know, Cambu, whether that answers your question. Camille, would you like to comment or? Okay, I guess he's happy. So Anthony is asking, are there experimental proposals to test which theoretical interpretation is correct? I think it will be difficult.
Yeah. So Anthony, I think I mentioned quickly a few things. So the LHC experiments can look in this very low mass channel for possible supersymmetric particles. The LHC experiments can also look for leptoquarks, which are, as I mentioned, my second favorite interpretation. And I also mentioned this experiment looking at hadronic vacuum polarization, the egg-shaped blob in the space-like region, which I think is very interesting. I should also mention that there is this experimental effort underway to see whether there is a similar anomaly in the anomalous magnetic moment of the electron. Now, at the moment, it's not possible to be sure because there's an important uncertainty in the fine structure constant. Now, that uncertainty is not important for the anomalous magnetic moment of the muon, but the anomalous magnetic moment of the electron is much smaller, and then this uncertainty in the fine structure constant becomes important. And so there's an effort underway by atomic physicists to measure the fine structure constant more precisely, as well as measuring the anomalous magnetic moment of the electron more precisely. If we then have measurements of both the electron and the muon, then by comparing the two, that could help us distinguish between different models. So for example, a leptoquark model, speaking off the top of my head, I think might make a different prediction from a supersymmetric model.
All right, thanks. Oh, in the meanwhile, Cambio says that it's actually great, that gives him some idea about how reliable the current lattice gauge calculation are. Luis has another question. With the amount of data expected for the high luminosity LHC, are there any proton-proton measurement which could be especially enlightening or complementary to the muon G-2 result?
Okay, well, I think I'm in danger of repeating myself again, but I think that one of the things to do is to, as I mentioned, extend the leptoquark searches to higher masses. In terms of supersymmetry, I think that pushing the limits on the masses of squarks and gluinos to higher values is not going to be directly relevant, because the squarks and the gluinos are not making contributions to G-2. If one wants to probe the supersymmetric interpretation of G-2, one really has to focus on this region here, where there is a small difference between the muon and electron masses and the neutralino mass. That's the region that we need to concentrate on.
Okay, thank you very much, John. Is there any other questions or comments which people would like to ask or just comment on something? Sounds like everyone is happy in the end. Okay.
Well, can you hear me?
Yes, absolutely.
Okay, John, I'm a slow typist. Actually, I have another question for you. You mentioned that, okay, there's a new effort in measuring the G-2 of the electron. So how does this, okay, say, new measurement of, say, the anomalous moment of the electron can shed light on the anomalous moment of the muon? I thought when you go to the high level, okay, they are not quite the same, right?
Okay, so in many models, the non-standard model contributions to the electron and muon anomalous magnetic moments are related by the square of the masses. So the contribution to the electron would be suppressed by ME divided by MU quantity squared compared with the contribution to the muon. And that is the target which the experiments on the electron are aiming at the moment. Now, as I mentioned, there's an issue with the uncertainty in the fine structure constant. And currently, that uncertainty is comparable with this quote-unquote prediction in many models for the anomalous magnetic moment of the electron. So we need the atomic determination of the fine structure constant to improve just by a small factor, and then we'll have a better idea of what's going on. Does that answer your question?
Yes. Okay, thank you.
Okay, thanks very much. So please ask more or just speak up or raise your hand, whatever is more convenient for you.
So while you're thinking, I'll quickly try to find a plot which it illuminates this point that we were just discussing. Okay. Okay, you see my slide?
Yeah, we can see it.
Yeah. So this is actually a picture taken from a paper on quantum sensors that was submitted to the SNOMAS sort of party a few days ago. And I'm actually a co-author of this SNOMAS contribution, although I didn't contribute to this particular part of the discussion. Anyway, this is just illustrating the most recent measurements of the fine structure constant and GE minus 2. And so here is, for example, a blow up of the measurement of current measurement of the anomalous magnetic moment of the electron. And here for comparison are various determinations of the fine structure constant using various different atomic measurements, using rubidium and cesium in particular. And you see that there was confusion here. If we had confirmation of this measurement here, and if the determination of the anomalous magnetic moment of the electron could be improved by a factor of 2 or 3, then we'd have a much clearer picture of what's going on with the electron. So that's, I think, a priority item for the atomic physics community to work on that.
Yeah, no, certainly there's one experiment at Berkeley is trying to measure the alpha much better.
Right. So that's, I think, referring to this green experiment here, which currently indicates some discrepancy with the anomalous magnetic moment of the electron, indicating that there may be an anomaly in the anomalous magnetic moment of the electron, which would be good news. However, there is this discrepancy with the value of alpha obtained in this rubidium experiment. And this needs to be clarified.
Now there's a new proposal trying to measure alpha. I don't know the detail because it was proposed roughly about a year ago.
Yeah, yeah. So my sense is that these atomic experiments are advancing pretty rapidly, and of course, the time scale is shorter than these big particle physics experiments, and there's various different avenues that can be followed. So I'm actually quite optimistic that within a few years, we're going to have the situation with the anomalous magnetic moment of the electron clarified. So at the moment, my attitude towards it is wait and see, but there may indeed be something interesting to see in a couple of years' time.
So thank you, John.
Yeah, so this is the snowmass review paper that I was referring to.
Yeah, no, I see. No, the Hogarth is on the offer list. Yeah, that's okay. He is now pushing a new measurement of alpha.
Okay, so you said Jason Hogan?
No, the Hogan Mueller.
Hogan Mueller.
Yeah.
Yes, yes.
Yeah.
Okay, this is a more general question on the chat. Luis is asking, what's your view on the main challenges on the theory side for next years?
Well, I'm going to have to say dark matter. So, there's all sorts of theoretical motivations for physics beyond the standard model, like naturalness and the hierarchy and grand unification and so on and so forth. But, these are all very, theoretical arguments. One, really big, well-established scientific fact is the existence of dark matter. And quite frankly, we have no experimental clue what it is. We've got an enormous number of theoretical ideas. So on the one hand, it's an experimental challenge to figure out what it is. On the other hand, I think it's a theoretical challenge to figure out ways in which the experiments can cast light on dark matter. And it might be, as I've discussed, some massive particle that can be produced at the LHC, and Kirill and Lewis and his friends, you're looking for that. But it could very well be that the dark matter is composed of coherent waves of ultralight bosonic particles, like, for example, the axion. And that, I think, is a very active theoretical area at the moment, with people trying to propose new ways of looking for axion-like particles in various different ranges of parameter space.
So Luis actually just clarified his question. Apparently it was he meant within the G-2 calculation, so he used the theoretical uncertainty. So he was not that general after all.
Oh, okay. Well, anyway.
but the general answer was great, he says.
Okay, well, as far as G-2, I think that the most interesting theoretical avenue to pursue is this optimization of the combination of data-driven and lattice calculations. And so I think that what needs to be done there is the most precise possible checks that the lattice calculation indeed does reproduce the data in this intermediate scale region, and then work on refinements of the integration of the extrapolation to small distances and large distances using the available experimental data. So I think this is a very promising way of clarifying the theoretical situation. And I know that a lot of people in the lattice community are working on that at the moment.
Thank you. Okay, any more questions or comments? Oh, I don't see any, so I guess everyone's happy. So thank you very much, John, for this enlightening lecture and all the explanations. I think that was very, very useful for everyone. So thank you very much again. And I hope the situation will allow us to have a face-to-face seminar soon. Yeah.
Yeah, all right. I hope also it'll be possible to have a visit in person to Hong Kong. And at least, Kirill, maybe we can meet face-to-face.
Yeah, absolutely, yes. I'm certain. All right. Okay. Thank you very much.
Thanks for the invitation. And,